Welcome to this presentation. Time has now come to introduce the concept of discrete sequence, Ztransform, and digital filter. So the new key concept we will meet in this presentation is discrete sequence and the Ztransform of a discrete sequence, and also the digital filter that transforms an input signal to an output signal. We start with some reflections. Computers use models to process discrete inputs to discrete outputs. Also, since modern data acquisition systems are usually computer-based, the data acquisition systems sample signal at discrete times, meaning that all real continuous signals are sampled at certain times, given by the sampling frequency, and when we start the measurement, of course. So, all measured signals can be seen as a discrete sequence, with values only at certain times Tn. So, from the perspective of a computer model, we are really looking for a model that responds with a response sequence xn to an excitation sequence fn. So that would be the kind of model we are looking for. So, for example, if we consider a 2-degree of freedom system, where we excite mass m in this case with force F, and we measure the response in x here. So how can we then model this system as a discrete system, with discrete sequences? Well, we start as usual with the governing differential equations for the displacement x. And if we state the two equations of motion here for the two masses, and then solve for the displacement of mass 1, then we will find this fourth order linear differential equation. You see, it's fourth order derivative here with respect to the displacement x, and in the right hand side we have the second derivative with respect to the exciting force F. So, in order to formulate this as a finite difference equation, we approximate all time derivatives with finite differences. So that means that we introduce the difference dx and difference df as the difference between two neighboring samples in the sequence, in the displacement sequence like this. So the fourth order difference then is of course a combination then of these sampled values of the signal. So the left hand side of our differential equation can be written in this form. See, it's a linear combination of the sampled signal xn down to xn minus 4. And the right hand side can be written, since it contained a second order time derivative, can be written in this form. Now the coefficients a and b here is of course depending on the mass and stiffness and damping coefficients, and also the time step. So how can we now relate the sampled signals to the Laplace domain? Remember that we usually like to work in Laplace or frequency domain. Well, that is achieved with the Ztransform, because the Ztransform is the discrete version of the Laplace transform. So it's developed to work on, well, to be applied to finite differences. So for a causal system, the Ztransform is defined as this. So we have the time sequence xn, and if we apply the Z-transform, we obtain the Z-transform of x. And as you can see here, the Z-transform is simply the sampled signal values times Z to the power of minus n, where Z then is a complex valued number. So this is the definition of Z-transform. And for a causal system, for a non-causal system, the lower index here is minus infinity. A causal system has the property that it is 0 before time equal to 0. So that means if we have a causal system, the sum starts at n equals 0. Before this, the signal sequence is 0. So, to continue, we have a very useful property of the Z-transform, and that is timeshift operator. If we shift the signal sequence m samples, then we obtain its Z-transform by multiplying Z raised to the power of minus m, and we multiply this with the original Z-transform. So time here, the time axis is shifted m times delta t increments in this case. And this can be compared, to the Laplace and Fourier versions. If we have take the Laplace transform of a time-shifted signal, where the time shift is minus a, then we can obtain its Laplace transform by multiplying the original Laplace transform with e raised to minus as, where s is the Laplace variable. And the Fourier version is like this. You multiply the original Fourier transform with e raised to minus I, the imaginary unit, times I omega. So this, as you know, is a phase shift. A omega is a phase shift. And in the Fourier domain, A omega, the phase shift, corresponds to the time shift in the time domain. So it can be found that the Z-transform has corresponding versions of all rules that is applicable to Laplace and Fourier versions. So this is one example of this, the shift operator. And it will be, as will be seen later on, this is very, very useful. So let us now apply the Z-transform to our governing difference equation. This was the right and left hand sides, and we now apply the Z-transform to the left hand side. We obtain this Z-transform, and to the right hand side then we obtain this version. And if we simplify, we extract the Z-transform of the displacement and the exciting force, and we can also write it like this, like the displacement transform is a factor times the excitation transform, and this factor we denote by h of z, and then we have introduced now the transfer function of the system, h of z. So like before, like in the Laplace domain, the Z-transform of the displacement is the transfer function times the Z-transform of the exciting force. So it's completely analogous to what we have seen before. And in a graphical form you can view it like this. So, from a digital filter perspective, we are looking for the digital filter H that responds with an output sequence xn, the displacement sequence, to the input sequence fn. So we have here now our schematic picture, and if we excite this system, if we feed the system now with an input exciting force sequence f, then as the measured output, as the responding output, we will be able to measure the displacement sequence xn. So, from an experimental modal analysis point of view, we wish to determine the mode parameters from measured transfer functions. Or we want to determine the digital filter coefficients that converts our exciting force sequence to the displacement sequence xn. And from these coefficients we can determine the mode parameters that defines our modal, our modal model of the system.